Good afternoon. My name is Tolbert Cavalli, and this is my controls final project. My project is a quarter car active versus passive suspension system that uses LQR and Kalman filters. The purpose of this project is to design and validate an optimal active and passive suspension control system for a quarter car model and compare them both to examine which one is better. The key objectives were to reduce body acceleration up to at least 40% in the active system compared to the passive system and maintain tire contact by limiting deflection to under 8 millimeters. It was also to ensure actuator force stays within plus or minus 1500 newtons. To achieve this, we applied LQR control to balance effort, comfort, and handling. And we used a Kalman filter to estimate unmeasured velocities and validate and basically use simulation to validate we use Simulink to validate the simulation with road disturbances. So for this project, we had to model the physical system, and the model for our quarter car approach was a sprung mass which is about 300 kilometers, and that is the vehicle body, and an unsprung mass, which is the wheel assembly part of the project, which is about 60 kilograms. And the suspension basically includes a spring with a stiffness of 16 kilonewtons per meter and a damper with 1.2 kilonewtons per second. Our control objective was to improve ride comfort, which minimizes body acceleration, and also maintain tire contact with the road for stability. For actuation, we have a force range of plus or minus 1500 newtons, which is our saturation limit, and this ensures the actuator operates safely within this design capability. We also impose a rate of 10 kilonewtons per second to prevent hydraulic lag for stability. Also, for sensing, we had three key measurements, which one was suspension travel, which was the difference between the sprung and unsprung mass displacement. And this, if you were to do this project in person physically, which we unfortunately couldn't do, but if you could do this project physically, you would need an LVDT or a string potentiometer to measure the suspension travel, and you would also need a secondary LVDT to measure the wheel displacement and a body accelerometer for the acceleration to measure the ride comfort assessment and validation. So for the quarter car active suspension, the control challenge is inherently multi-input, multi-output in nature, and this slide highlights that our quarter car model has two dominant vibrational modes. And the two modes are a low frequency body mode at around 1.2 Hertz and a high frequency wheel hub mode at around 9 Hertz. While we didn't really explicitly design the control around these exact frequencies, they illustrate why a more advanced MIMO controller like the LQR is suitable for this project, because it can handle both ride and comfort and road holding, which is something a simple loop PID would struggle with. We also use a Kalman filter which supports this idea by providing accurate state estimates in the presence of sensor noise. This slide shows the performance targets we set before starting the design, and in the context of my project, good performance means delivering a ride that is both comfortable for passengers and safe for vehicle handling. And this all has to be done while respecting mechanical and actuator constraints. So first, for peak body acceleration, the passive suspension baseline is 2.5 meters per second squared, and our active target was 1.5 or lower, which is about a 40% reduction to improve comfort. For the RMS body acceleration, which basically reflects overall vibration exposure, my target was around 0.7 or lower, and that is again about 40% or better than the passive suspension system. Here we compare the passive and the active quarter car suspension modes, and I draw a free body diagram to show what the passive suspension system looks like and what the active suspension system looks like. And the key differences are that the passive system is a spring mass damper system, and the active system includes an actuator. As you can see here, it has a spring, a damper, and an actuator for the whole entire system. And I'm going to show you later on how this was designed in both MATLAB and Simulink and what results we got from it. This is the state space modeling that I did. These are the state space models and the equations of motion that I used. For example, this first equation, it shows the sprung mass, which includes spring force, damper force, and actuator input. And the second equation is the unsprung mass, which also sees the tire stiffness and the opposite of the actuator force. And basically, I group these equations into a state vector, which shows the positions of both masses transposed. This slide also shows the equations of motion, but basically here we rewrite them into matrix form, whereby the A matrix contains the system dynamics, which basically shows how positions and velocities evolve without control, and the B matrix defines how the actuator force enters the system, while the E matrix shows how road disturbances affect it. And here below you can see the output equation, which uses the C matrix to extract the data that we need. So why LQR and Kalman? I chose LQR because it optimally balances comfort by minimizing body acceleration with control effort, and it is also the one that handles coupling between body and wheel dynamics in the MIMO system. For the Kalman filter, it lets us estimate velocities without extra sensors like tachometers, which keeps the cost down, and it is also robust to noise, which we assume to only be around 1 millimeter standard deviation. So why not PID? PID was avoided because single loop PID struggles with road disturbances, and the multi-mode nature of this project has a lot of it has a lot of inputs and a multi-mode, so PID wouldn't be suitable for such a project. This is my Simulink design, and as you can see here, we have a plant system, which is the exploded view of the plant subsystem highlighted in blue here. And basically the plant system is the passive suspension system, and that this is how I designed it. And this second system that makes the passive system as a subsystem is the active system, and it is designed by basically adding a Kalman filter and an LQR again with a saturation of about plus or minus 1500 newtons. That is what really creates the active system, because the Kalman filter sort of mimics the actuator design in this project. These are the result plots from the Simulink design that you saw earlier, and here I know they look a little bit similar, but they are very different. And as you can see here with the peak levels, you can see that there are different damping effects. Basically, these plots show the vertical displacement of the sprung mass representing the vehicle body, and the unsprung mass, which is the wheel assembly, after a disturbance. Both reach an initial peak of around 9 millimeters before settling within 3 seconds, and the sprung mass stabilizes around 6.7 millimeters, while the unsprung mass settles at slightly 5.9 millimeters. So for the Kalman filter design, we set a small process noise covariance QN to reflect minor model uncertainties, and a sensor covariance RN, which is based off of the 1 millimeter measurement resolution that we talked about earlier. This filter basically estimates the full vehicle state without direct velocity measurements, making it cost effective and noise robust. And it does this by combining it with the LQR gain, which forms the LQR controller that tracks the true states that happen in the actual project despite the noise. So these are the Kalman filter results, and these results effectively reduce noise and help us to closely track the true dynamics of our project. Here you can see for directly measured variables such as the wheel hub position and the suspension travel, the Kalman filter smoothes the noisy measurements without introducing any noticeable delay. And for the unmeasured states such as body velocity, it provides accurate reconstructions that closely match the true behavior that we're looking for. Here in this slide, we compare the active and passive suspensions, where the LQR controller shows a slight increase of 2.6%, which is an increase in peak body acceleration, and almost no change in the root mean square acceleration, which is the RMS acceleration. The suspension travel and tire deflection seem to remain unchanged, and the control force also stays within our limits. So this is another plot that compares acceleration between passive and active suspension. And here you can see that the passive suspension is shown in the dashed black line, and the active LQR suspension is in the solid red line. And we can see that the active control slightly lowers the peak acceleration right after the disturbance, and it allows the system to settle a bit faster, while the improvement is modest. The smoother curve from the active system remains fewer. It remains less abrupt, like it has less disturbances. Here we compare suspension travel and tire deflection for both passive and active. Passive shown in the dashed black and active LQR shown in the solid red. And in both cases, the active system slightly reduces the oscillations and settles faster than the passive setup. This is also another MATLAB plot that shows the control effort, which was saturated at the plus or minus 1500 newtons, which I also modeled in Simulink, as you will see later on. So basically this plot shows the actuator force applied by the active suspension system with saturation limits, like I said, for plus or minus 1500 newtons, and the control effort basically peaks at around negative 20 newtons immediately after the disturbance. So for the limitations of this project, we had some limitations and extensions, and basically the first limitation is this is a simplified model. It only captures vertical dynamics and ignores pitch and roll, ignores load transfer. Another limitation is that we make linear assumptions when making this project, which neglects real-world non-linearities like damper valve behavior and geometry changes and friction. Also, this is a reactive-only project, meaning without road preview, we can't really make preemptive adjustments. And while the Kalman filter improves sensor reliability, it lacks fault detection capabilities. So that is also a limitation that we have in the Kalman filter. So looking ahead, there are several improvements that we could make for this project, and one of them could be full vehicle control with a 7 degree of freedom model, and this could be a lot more complicated, but this could help and help us understand more about this project. Basically, the key takeaway is that the LQR provides a solid foundation, but it requires addressing higher order dynamics and non-linearities for real-world deployment, which are not possible for a project like this because it's a lot more simplified. In conclusion, I learned that the comparison between active and passive suspension differences is very minimal, and this explained why most cars use passive suspension. Our LQR controlled active suspension improved comfort by reducing body acceleration peaks and settling time, and it also maintained better suspension travel control compared to the passive system. I also learned that the Kalman filter effectively smoothed the noisy measurements and estimated the unmeasured states, enabling LQR to apply the precise control forces that we needed. Thank you. That was my project.